In this video, we are going to talk about inner product and orthogonality, and along the way, we will talk about length and distance. This here is the overview slide, which we will spend 3 or 4 minutes going over before we then go over each topic in more detail and with more examples. The inner product is a generalization of the dot product, and the dot product that we use for vectors in Rn. So just to review, the dot product for vectors in Rn, if you have two vectors u dot v, if you consider u, the vector, to be a matrix with only one column, and v, a vector, a matrix with only one column, then u dot v can be defined as u transpose multiplied by the matrix or vector v, and which we can write out that formula will give us component by component multiplication all added together. So u1 v1 plus u2 v2 plus up to un vn. The dot product then for vectors in Rn is an example of an inner product. So in general, an inner product are if you have vectors u, v, and w, not necessarily in Rn, but you have vectors and a scalar c, then the inner product is a function that assigns a scalar to each pair of vectors u and v that satisfy, this function satisfies these 4 conditions. 1, there's this commutativity, u dot v equals v dot u. 2, there's this distributive, so w dot u plus v is equal to the sum of u dot w, and v dot w. We have this scalar that you can pull it out. So scalar c times a vector u dot v is equal to the scalar c times u dot v, which is equal to u dot the scalar c times v. Then last, if we take an inner product with itself, so u dot u, it's always greater than or equal to 0, and only equal to 0 if and only if u is equal to 0. From the definition of the inner product, we get the definition of the length, also called the norm, so these two terms are interchangeable. Length or norm of a vector v is the non-negative scalar, which we denote with these kind of absolute value signs. So absolute value, or the norm of vector v, is equal to the square root of the dot product of v with itself. A vector whose length is 1 is called a unit vector, and if we divide a non-zero vector by its length, that is, if we multiply by 1 over the norm of v, we obtain a unit vector, and this process is called normalizing the vector, and the direction is preserved. The direction of the original vector is preserved. We have the distance formula. Once we have the length, we can define a distance formula for two vectors, u and v and Rn. So the distance between u and v, written dist uv, is the length of the vector u minus v. That is, distance of uv is equal to the norm of u minus v. In R2 and Rn, this definition coincides with the usual formulas for Euclidean distance between 2 points. From the inner product, we can define orthogonal vectors, and when we talk about orthogonality of vectors, that's the generalization of the concept of perpendicular lines in ordinary Euclidean geometry. So we say two vectors, u and v and Rn, are orthogonal to each other if u dot v is equal to 0. So this is our definition, but it does have this generalized concepts of perpendicular. Note the 0 vector is orthogonal to every vector in Rn, and we also have this Pythagorean theorem that two vectors u and v are orthogonal if and only if the Pythagorean theorem here applies. That is, the norm of u plus v squared is equal to norm of u squared plus norm of v squared. Last, we will talk about orthogonal complements, which we'll bring up again when we talk about singular value decomposition in another chapter, future chapter. So if z is orthogonal to every vector in a subspace W of Rn, then z is said to be orthogonal to the subspace W. The set of all vectors z that are orthogonal to W is called the orthogonal complement of W and is denoted W perpendicular with this perpendicular sign written over here, also called W perpendicular or sometimes W perp for short. So some properties and facts: a vector x is in W perp if and only if x is orthogonal to every vector in a set that spans W, and 2, W perp is a subspace of Rn. And then last we have this theorem. If A is an m by n matrix, then the orthogonal complement of the row space is the null space of A, and the orthogonal complement of the column space of A is the null space of A transpose. So I have this rewritten here. The row A perp is equal to null of A, and column A perp is equal to null of A transpose. So that's it for our overview. So we'll go back and start with inner product. We are going to start with the definition of an inner product, and the inner product is a generalization of the dot product as we will see. But remember, our vectors need not be vectors in Rn, right? We talked about different types of vectors. And so let's say we have three generic vectors, u, v, and w, and c is a scalar. Then an inner product is a function that assigns a scalar to each pair of vectors, u and v, and satisfies these four properties. First, there's this commutativity, so u dot v is equal to v dot u. Second, there's this distributive property. The dot product of w with the sum of u and v is equal to the sum of the dot product uw and vw. Next, we have this way of pulling out constants. So the dot product of v with cu is equal to c times the dot product of u and v, which is equal to u times u dotted with cv. And last, the dot product of a vector with itself, u dot u, is always greater than or equal to 0, and it's equal to 0 if and only if u is 0. This first example is a general inner product for polynomials of degree 2 or less. And I included this example even though it is not in your book because I feel like it's important to demonstrate there are other inner products other than the dot product for vectors in Rn. So here our vectors are polynomials of degree 2 or less. So we have for polynomials pt and qt in P2, we want to verify the following is an inner product. So we're going to define, again, to define an inner product, it's going to assign a scalar to our two vectors. So p dot q is equal to the integral evaluated at 0 and 1 of p of t times q of t dt. The first thing to notice is that this definition of an inner product does assign a scalar. By the time you do the integral and plug in the endpoints, you will have a scalar or real number as your answer to the inner product. To verify this function is a dot product, we have to show that it satisfies the four conditions. So the first condition is the commutativity. So in other words, plugging in the definition now of our inner product, so u dot v is defined to be the inner product from 0 to 1 p of t times q of t dt. And we want to show that that's equal to v dot u, which is equal to 0 to 1 q of t times p of t dt. And this is certainly true because of the multiplication properties of polynomials. In other words, p of t, q of t is equal to q of t, p of t for polynomials. For our second property b here, we're going to look at u plus v dot w, and we want to show it's equal to u dot w plus v dot w. So I have it written here. So I'm going to start by saying, well, we're going to let our vector u here be a polynomial of degree 2 or less, and our vector v here also is a polynomial in t of degree 2 or less. And last, w is a polynomial of degree 2 or less. So looking at the left-hand side of the equation of the property we want to show, we're going to get u plus v dot w. So that's going to be the integral. Well, first we have u plus v, so u of t plus v of t dotted with w, so multiplied by w dt. So again, I'm just plugging this in to my definition of my inner product. And when I do the algebra, algebraically, this I can multiply my polynomial wt times u of t and then wt times v of t. And then again, because of properties of derivatives, I can break this up into two integrals, sorry. So I have my first integral, 0 to 1 u of t w of t, and second integral, 0 to 1 v of t dw of t, which is equal to u dot w here, and the second integral is equal to v dot w. So I have proven this second property. This third property, c, with the constant, I have done proof by assignment. That is, I have left that as an exercise for you. And to prove this last property that u dotted with itself is always greater than or equal to 0 and only equal to 0 if u is equal to 0, I relied on the fact that, well, first I did u dot u, and I showed that it's equal to the integral from 0 to 1, u of t squared. And I'm relying on the fact that the integral can be interpreted as an area under the curve. And since it's an area under the curve, it's always greater than or equal to 0. And finally, it's only equal to 0 if u of t is equal to 0. And by showing these four properties, I have shown that this function here is indeed an inner product. For the rest of this video and chapter in your book, when we talk about inner product, we're going to talk about dot products of vectors in Rn. So we can define u dot v if we consider U a matrix with only one column and V a matrix of only one column, then we can define U dot V as matrix multiplication of U transpose times V, which gives us this formula here, U1 V1 plus U2 V2 up to UN Vn. Our first example is to compute U dot V and V dot U for U equal 2, -5, -1, and V equal to 3, 2, -3. So here we have U dot V, so we can take U transpose, which is 2, -5, -1, and multiply it by 3, 2, -3. And by matrix multiplication, that will equal to -1. We can also do V dot U, so I took V transpose and multiplied it by U, and then by matrix multiplication, I also get -1, which, remember, according to our properties of an inner product, this dot product is commutative. For our next example, we are going to verify the dot product for R2 is in fact an inner product. So in other words, we're going to verify that the dot product for R2 satisfies these four conditions for a inner product. I'm going to start with two representative elements of R2, which is U1, U2, and V1, V2, and take the dot product. So I'll get U1, V1 plus U2, V2. To establish this first condition that U dot V equals V dot U, I will compare my U dot V to V dot U. So V dot U, I take V transpose multiplied by U, and I get V1 U1 plus V2 U2. Now, because these are two real numbers, the V1 and U1 are both real numbers, multiplication of real numbers commutes, so I can change this to U1 V1. Similarly, for V2 U2, it can become U2 V2, and this here is simply U dot V. So what I have shown is that V dot U is equal to U dot V. The next property, I am going to do proof by assignment. That is, I'm going to leave it as an exercise for you. I will do part of property C here, which says that a constant C times vector U dot V is equal to the constant C times U dot V. And the second part I will also leave for you. So I have CU dotted with V. So CU is the constant C times my vector U, and then to dot it with V, I'm going to multiply it times my V vector. So C times U will give me CU1, CU2, dotted with V1, V2. So what this gives me is CU1, V1, CU2, V2, and because these are now real numbers, I can pull out my C, factor out my C, and I get CU1, V1 plus U2, V2, which is simply C times U dot V. Next, I will show a vector U dotted with itself is always greater than or equal to 0. So here I have U dot U, so I have U transpose times U, which gives me U1 squared and U2 squared. And as long as U1 and U2 are real numbers, this will always be greater than or equal to 0. And also for real numbers, it's only equal to 0 if U is equal to 0. So I have shown most of these four properties. I have one more property to show, which is over here, an asterisk, but I am going to use my properties of inner product to prove this. So I have C1U1 plus C2U2 plus up to CPUP dotted with W is equal to C1U1 dotted with W plus C2U2 dotted with W plus up to CPUP dotted with W. So here I've just rewritten the left-hand side of the equation, C1U1 plus C2U2 plus up to CPUP dotted with W equals, well now on this side, what I can do is I can peel off my C1, U1, my first vector, and consider the addition of all these vectors. Well, addition of a bunch of vectors gives you a second vector. So here's one vector plus another vector dotted with W. So now I can use part B here. I have two vectors added together dotted with W, and that's my first vector dotted with W plus my second vector dotted with W. So here I have C1, U1 dotted with W, and then my second vector in parentheses dotted with W. And I can do this repeatedly until I get C1, U1 plus W plus C2, U2 plus dotted with W plus up to CP, UP dotted with W. And then finally, using part C over here, I can take out my constant. So I can do my U1 dot W times C1, U2 dot W times C2 up to UP dot W times CP. And this right here is the right-hand side of my equation. Now that we've talked about inner product, we can go on to define the length of a vector v, also known as the norm of a vector v. And it's the non-negative scalar that we denote, the norm we denote with these absolute value signs of v is equal to square root of v dot v, which is equal to v1 squared plus v2 squared up to vn squared square rooted. A vector whose length is 1 is called a unit vector. And if we divide a non-zero vector by its length, that is, if we multiply it by 1 over magnitude of v, we obtain a unit vector in this process, and that's called normalizing. And notice when we normalize a vector, we preserve the direction, but we make the length equal to 1. So the first thing we just want to look at, again, is the length. And if we look in R2, so if we have a vector here where it's x units along the x-axis, y units along the y-axis, by the Pythagorean theorem, the length of this vector is going to be square root of x squared plus y squared. So here I have the length of v is equal to square root of x squared plus y squared by the Pythagorean theorem, and then that's exactly equal to our magnitude of v defined over here in terms of our square root of v dot v, which is equal to xy dot xy, so it's x squared plus y squared. Similarly, in R3, we can use the Pythagorean theorem to show that the length of v is equal to the square root of v dot v. Our first example for length, let v equal the vector 1, negative 2, 2, 0. We want to find a unit vector u in the same direction as v. To get a unit vector in the same direction, we need to divide by its length. So the first thing I need to do is calculate the length of v. I calculate the length by taking the square root of the inner product. So here I have v transpose times v, and I get square root of 1, and then negative 2 times 2 is 4, 4, and 0, which gives me a length of 3. Then my unit vector u is equal to 1/3 my original vector v, 1, negative 2, 2, 0. Or in other words, this 1/3 minus 2/3, 2/3, 0. You can verify now that u is unit length or has a length of 1 by taking the inner product of u dot u. And you also know that u is in the same direction as v, since u is simply 1/3 of v, or u is equal to 3v. So you know that u is simply a scalar multiple and therefore in the same direction as v. Our next example is let w be the subspace of R2 spanned by the vector x equal to 2/3 1. Find a unit vector z that is a basis for w. I started just by writing this out. W is equal to the span of this vector 2/3 1. So in other words, it's every linear combination of this vector, which is just C1, times 2/3 1. This is what W is, all linear combinations, or all multiples actually now of this one vector. I found the length of the vector by taking the square root of the inner product of x with itself, which is equal to, the length was equal to square root of 13 over 9, which is kind of an ugly term. But I saw your book does this, and so this makes a lot of sense. What you can do is you can simplify this. So instead of looking at the span of 2/3 1, you can look at the span, just multiply this vector by 3, because the span is equal to any constant times this vector. So in other words, multiply the whole vector by 3 and you get this span is equal to the span of 2, 3. So now we have nicer numbers to work with. Now the length of our vector 2, 3 is equal to the square root of 13. So our vector z, our unit vector z that is a basis for w, is equal to 1 over square root of 13 times 2/3, which is 2 over square root of 13, 3 over square root of 13. And then last, again, we can verify the length of z is equal to 1, and also we can verify the direction. So the direction of z is just a scalar multiple of v. And the way I figured out what scalar multiple, just looking at this, to go from the bottom, to go from 1 to 3 over square root of 13, that means the scalar multiple must be 3 over square root of 13. And if it truly is just a scalar multiple, then this here, the 3 square root of 13 times 2/3 should equal to 2 square root of 13, which it does. So you can see that z then is just a scalar multiple of our original vector, meaning it has the same direction and the span will be the same. Now we can talk about a distance formula in Rn for the distance between u and v, two vectors, and we denote that with dist uv. And it's the length of the vector u minus v. That is, the distance between u and v is equal to the length of u minus v. And in R2 and R3, this definition coincides with the usual formulas for Euclidean distance between 2 points. I've moved my definition of distance up here, and I have our first example then. Compute the distance between the vectors u equals 7, 1 and v equals 3, 2. So the distance is the magnitude of u minus v, or the length of u minus v. So here I have u minus v is equal to 4, negative 1. Then taking the length of that is the length of 4, negative 1, square root of 4 minus 1 dotted with 4 minus 1, and that gives us square root of 16. And just looking at this in case it's been a while since we looked at vectors in the plane. So here's our vector u, and here is our vector v. When we do u minus v, we're going to add u to negative v. So here's my negative v. When we add u to negative v, we're going to do the parallelogram, so completing this parallelogram between u and v, or you can simply think of moving the beginning of the u vector to the end of v, or the other way around. But either way, this is the final point that you get over here. This is our u minus v, which is exactly what we calculated over here, the 4, negative 1, and then we can calculate the magnitude, which is equal to square root of 17. This next example is deriving a distance formula for two vectors in R3. So if we let u be a vector in R3, a generic vector, so we'll just name it u1, u2, u3, and v be a generic vector, v1, v2, v3, then the distance between u and v is the distance between, or the length of u minus v. So we have u minus v dot u minus v, so we're going to get, well, u minus v is just term by term subtraction. So u1 minus v1, and then because we dot it, squared, plus u2 minus v2 squared, plus u3 minus v3 squared. So again, this is just the derivation of the formula, the distance formula, for 2 points in R3. Leaving the idea of length and distance for now, we're going to talk about orthogonal vectors. So orthogonality of vectors in Rn is the generalization of the concept of perpendicular lines. So we say things are perpendicular sort of interchangeably with orthogonal. Orthogonal, again, is the generalization. So two vectors u and v in Rn are orthogonal to each other if u dot v equals 0. Note the 0 vector is orthogonal to every vector in Rn. We're going to look at this definition in R2 and show that it's true that two vectors are orthogonal or perpendicular if u dot v equals 0. So again, we're going to consider R2. We're going to look at two lines for the origin determined by the vectors u and v. And what we are going to use is this fact here from geometry, which you probably haven't looked at in a few years. But this is what we're going to use. So the two lines, we're looking at the line U and the line V. So the two lines are geometrically perpendicular if and only if the distance from U to V, this line in blue here, is the same as the distance from U to negative V, this other line in blue. So if this distance equals this distance, we can say U and V are perpendicular. And I realized I need some more space, so I moved things around. I have my picture over here, here's my UV, and I want to prove these two blue distances are the same. I have my statement here, and then and additionally, the two lines being geometrically perpendicular if and only if the distance from U to V is the same as the distance from U to minus V. This is the same as requiring the squares of the distance to be the same. So we're going to start by calculating the distance from U to minus V squared. So here I am calculating the length of U minus negative V, which is essentially the length of U plus V squared. So that's going to be U plus V dot U plus V. And technically, you could probably figure out how to do this, but technically what I did is I used the second property of inner product. So if you go back, we had the 4 different properties that the inner product had to satisfy. This is the second property, property B. And it says when we have a sum of two vectors dotted with a third vector, so here I have a sum of two vectors dotted with, and I took this sum of two vectors to be my third vector. So altogether U plus V is equal to W. And then I applied this formula here, the right-hand side. And I get, that's U, my first vector here is U dotted with W, so I put in my W, plus V dotted with my W, which is my U plus V. Then I use this property B again to expand to this, and I get U dot U plus U dot V plus V dot U plus V dot V. And you really could have just multiplied this out and gotten the same thing, but technically you would want to be using one of those 4 properties. So here we have our length of U squared. Over here, V dot V is the length of V squared. And then we have a U dot V and a V dot U. These two are equal. That was our first property of inner products. So I'm going to say this is plus 2U dot V. Similarly, you can calculate the distance between U and V squared, and you'll get the length of U squared, the length of V squared, minus 2UV. Which means these two distances are equal if 2U dot V is equal to minus 2U dot V. I can cancel out my 2's, but now I have U dot V is equal to negative U dot V, which is only true when U dot V is equal to 0. So again, the two distances are equal if U dot V is equal to 0, and the two distances are equal only if they're perpendicular. So if it's orthogonal or perpendicular, then the dot product is 0. Now we have a way of testing if two vectors are orthogonal. We take the dot product and see if it's equal to 0. We also have this Pythagorean theorem, so two vectors U and V are orthogonal if and only if the length of U plus V squared is equal to the length of U squared plus the length of V squared. Our last topic of this video is orthogonal complement. So we're going to discuss this concept, and then later we will use it in a later video when we talk about singular value decomposition. So if a vector Z is orthogonal to every vector in a subspace W of Rn, then Z is said to be orthogonal to the subspace W. The set of all vectors Z that are orthogonal to W is called the orthogonal complement of W and is denoted with this W and this little perpendicular sign, perpendicular sign that we used to use in geometry. And we read this as W perpendicular or W perp, perp standing for perpendicular. I have my definition now of my orthogonal complement. Again, those are the vectors in Z that are orthogonal to my subspace. And I have this example with a picture. So let W be a plane through the origin in R3. So the plane is this green plane. The origin is this dot, 0 in black, O for origin. And let L be the line through the origin and perpendicular to W. So L is this blue line. If Z and W are non-zero and Z is on L, so we have this vector Z on L, and W is in the plane, W, then the line segment from 0 to z, that's this line segment, is perpendicular to the line segment from 0 to w. So here's, and it's perpendicular, so we try to draw this right angle between the two. So z is on the line, and the line is perpendicular to the plane. So since z is on the line, it's going to be perpendicular to w, which is in the plane. So z dot w will equal to 0. So each vector on L is orthogonal to every vector w in the subspace. And in fact, L consists of all the vectors that are orthogonal to the w's in W, and W consists of all the vectors orthogonal to the z's in L. That is, L is the W perpendicular, and W is equal to L perpendicular. And just to kind of draw this, so what do I want to say? Each vector on L is orthogonal to W, so you can kind of see that because it's all in the same direction. But L consists of all the vectors that are orthogonal to the W's, right? So there's a bunch of W's, right? So here's another, let me draw them in red. Here's another vector on my plane, but they are all perpendicular to this L, this line. So that means my W perp, my L perp, those are the set of vectors that are orthogonal to L is equal to W. And then my W perp, again, those are the vectors Z that are orthogonal to W. That's all these different vectors along L. We have two facts or properties. A vector x is in W perp if and only if x is orthogonal to every vector in a set that spans W. And second, W perp is a subspace of Rn. And last we have this theorem: if A is an M by N matrix, the orthogonal complement of the row space of A is the null space of A, and the orthogonal complement of the column space of A is the null space of A transpose. So I have that written here. The row of A perp is equal null of A, and column of A perp is equal to null A transpose. We're going to start by looking at this picture here of what's going on. Here we have the row space of A. So in other words, if this is our matrix A, we're just going to look at a 2 by 2 just to be simple. And the row space is essentially the system of linear equations that get us here. In other words, the linear combination of each row is a11x1 plus a12x2. That's the first linear combination. And then the second linear combination. So the row space is a set of linear combinations of the row of A. Again, it's kind of the linear equation that this matrix represents, that matrix AX represents. So that's the row space. And then we have the null of A. Those are the values of X that get sent to 0 by A times X. And then over here on this other side, we have the column space of A. And the column space of A, right, after you transform your X by multiplying by A, what you get is your column, the first column of A times x1 plus your second column of X times x2. So this is all the linear combinations of the columns of A. In other words, that's the column space that we have over here. And again, the thing that maps from the row space of A to the column space of A is the matrix A, as you see here, the A times X. So before you are in the row space, when you multiply by A, you end up in the column space. I put the drawing over here for your reference, and we'll start the proof that the row of A perp is equal to the null of A, and also the column A perp is equal to the null of A transpose. I moved my drawing over here for your reference, and what we want to prove is we're going to prove the first part of this theorem, that the orthogonal complement of row A is equal to the null of A. And to do that, we're going to use kind of the standard techniques of proving these things from set theory. So if we wanted to prove that set A is equal to set B, the standard way to do this is to show that A is a subset of B, not a proper subset, not this type of subset. That's not what we're proving. We're proving that A is either contained or equal to B, and B is contained or equal to A, or B is a subset of A. And if both of these are true, that necessarily implies that A must equal to B. Now, to show this part, to prove that A is a subset of B, what we need to show is that if X is an element of A, then X must be an element of B, and that's enough to show that A is contained in B. We are going to use these two standard proof techniques to show that the row A perpendicular is equal to the null of A. So the two things we need to show equality from here is that row A perpendicular is a subset of null A, and the second thing is that null A is a subset of row A perpendicular. And starting with this first proof, or first part of the proof, to show that row A perpendicular is a subset of null A, that means we need to show if there's an element X in row A perpendicular, then X must also be in the null of A. That's how we show it's a subset, or yeah, a subset. And then second, over here, to show null A is a subset of row A perpendicular, means if X is in null A, then X must also be in row A perp. We are going to start with the first part of the proof to show that row A perp is a subset of null A. And to show this, we need to show if X is in the row A perp, then X is in null A. So we're going to start with let X be in the orthogonal complement of row A. That is, X then is orthogonal to each row of A. So I have this situation drawn out here. I have my matrix A and X. When I multiply it out, I multiply row times column, I get this first linear equation, row times column to get the second linear equation all the way down to the nth linear equation. And the thing is, every time I multiply a row times column, here what I get is my first row dotted with X, right? So this matrix multiplication is giving us, in the first row, it's giving us the first row of A dotted with X, and because X is orthogonal to each row of A, that must equal to 0. Similarly, the second row dotted with X is equal to this term here, or this coordinate here, and because X is orthogonal to each row, then that must equal to 0, all the way down to the nth row. The nth row dotted with X must also equal to 0. And looking at this as a whole, what that means is AX must equal to 0. So X must be in the null space. So what we have shown is if X is in the orthogonal complement of row A, that means X is in the null space. So this is exactly what we have shown. So we have shown that the orthogonal complement of row A is in the null space of A. Okay, now that we've done this part here, the first statement we have done, we're going to work on the second part of our proof, which is to show that the set on the right-hand side is a subset of the set on the left-hand side, or null of A is a subset of the orthogonal complement of the row of A. To show this containment, the subset thing here, we need to show if X is an element of null of A, then X must be an element of the orthogonal complement of the row of A. So I start with X in the null of A. So then AX equals 0, and I kind of drew what this looks like. So I have my matrix A, my vector X equals 0. I can multiply row times column, and I get this linear equation. I multiply row times column, I get my n linear equations, and that's equal to the 0 vector. And all of this is just another way of saying that AX equals 0. But now again, this linear equation here is equal to the row dotted with the vector X, and it's equal to 0. So that means X is orthogonal to this first row. And then the second row, when we dotted the second row with X, that's the second linear equation, it's equal to 0. That means that X must be orthogonal to the second row, all the way down to the nth row. When we multiplied the nth row times the column vector X, this is the row vector dotted with X is equal to this equation here, which is equal to 0. And since the dot product is equal to 0, that means X must be orthogonal to the last row. So again, X is orthogonal to each row vector of A. Since the rows of A span the row space of A, that means X is in the row A perp. So what I've shown is that if X is in the null of A, then X is in row A perp. So that's this second statement here. And since I've shown both the first and second statement, that means I have proven my equality of the two sets. I have one more problem example to show you, but since we've covered all the material now for this video, I'm going to suggest after the problem statement that you pause the video to give the problem a try before looking at the solution. Oh, I guess I lied. There are 3 more problems, but the first one's easy at least. Let A be the vector -2, 1, and B be the vector -3, 1. Compute A dot B divided by A dot A, and also A dot B divided by A dot A times the vector A. The second question is let C equals the vector 4/3 minus 1 2/3, and D be the vector 5, 6, -1. The first problem, part 1, is to find a unit vector U in the direction of C. Part B is show that D is orthogonal to C, and then the last part is use the results of A and B, parts A and B, to explain why D must be orthogonal to the unit vector U. The final question, let W be a subspace of Rn. Exercise 38 establishes that W perp is also a subspace of Rn. Prove that dimension of W plus dimension of W perp is equal to n. The first problem is fairly straightforward. We take A transpose multiplied by B, and we get -2 times 3 is 6, plus 1 times 1 is 1, so we get 7 for A dot B. And then A dot A, we have -2, 1 dot -2, 1, that's -2 times -2 is 4, plus 1 times 1, so we finally get 5. So then to calculate A dot B divided by A dot A, that's going to be just 7 divided by 5. And then if we multiply by the vector A, that's just 7/5 times the vector A, -2, 1, which is equal to -14/5 and 7/5, written as a vector in this fashion, -14/5, 7/5. Question 2, C is equal to 4/3, -1, 2/3, and D is equal to 5, 6, -1. Find a unit vector U in the direction of C. So to simplify things, I can multiply C by 3. So 3C is equal to 4 minus 3, 2. And we know that's in the same direction as C because they're just scalar multiples of each other. And then I can divide my 3C by the length of 3C to get a unit vector. So I do my 4, -3, 2, dot 4, -3, 2 square rooted, and I get the square root of 29. So that's the length of 3C. So U is a unit vector, 1 over square root of 29, 4, -3, 2. And you can verify that this is unit length, and you can also verify that U is simply a multiple of C. But I'll leave that to you. We did a similar problem in the video. So next, show that D is orthogonal to C. So what we need to do is take the dot product of D with C. So here is D, 5, 6, -1. And then C is our 4/3 minus 1, 2/3. And you can see the dot product is equal to 0. Last, use the results of A and B to explain why D must be orthogonal to the unit vector. Well, D is orthogonal to C, and U is a scalar multiple of C. So D dot U is equal to D dot, and U is equal to our 3/29th C, right? Again, U is just a scalar multiple of C. So we can pull out our scalar multiple, and we get D dot C. So we have D dot U is equal to 3 over square root of 29, D dot C, but D dot C, we've already determined, was equal to 0. So this whole thing here is equal to 0. So that means D dot U is also 0, and D and U are orthogonal. The last problem, let W be a subspace of Rn. We know that the orthogonal complement of W is a subspace of Rn. We want to prove that the dimension of W plus dimension of W perp is equal to n. I also copied this theorem here for your reference. First, if W is equal to only the 0, then W perp is equal to Rn because the 0 vector is perpendicular to everything. So if W is not just the 0 vector, we're going to have a basis for W. And let's say that the basis has P elements, B1, B2 up to Bp, where P is between 1 and n. It's a basis for W. We're going to make a matrix A using these basis vectors to form the rows of A. So in other words, the first row is B1 transposed. The second row is the second basis vector transposed up to BP transpose. And by the way, A is a P by N, right? There are P rows because there are P basis vectors, and N because these bases cover Rn. So now W is the row space of A because we constructed A from the using the basis of W to become the rows. So W equals row of A. So W perp is equal to row A perp. Let me get rid of this extra parentheses. So I'm going to now use this theorem here that we copied from earlier in the chapter that says row A perp is equal to the null of A. So according to this, then W perp, which is equal to the row of A perp, is equal to the null of A. So again, W perp, which is equal to row of A perp, which says this is equal to null of A by the theorem. So that means the dimension of W perp is equal to dimension of null of A. And then we have the dimension of W plus the dimension of W perp. Well, W is equal to row A, so that's the dimension of row A plus the dimension of null of A. And then we know from the rank theorem that the rank of A is equal to the nullity of A, which means it's equal to n. So now dimension of row of A plus dimension of null of A is equal to n. To summarize what we covered in this video, we talked about an inner product, and the inner product is a function that assigns a scalar to each pair of vectors u and v that satisfies these four conditions. First, there's this commutativity, u dot v is equal to v dot u. Second, there's this associativity, so u plus v dot w is equal to u dot w plus v dot w. There's this thing with the scalars, you can factor it out, so a scalar c times u dot v is equal to c times u dot v is equal to u dot cv. And then last, a vector dotted with itself is always greater than or equal to 0 and only equal to 0 if u is equal to 0. So these are the four properties of an inner product. And then we also said that the dot product of vectors in Rn is an example of an inner product. And so the dot product of two vectors, if the vectors are in Rn, is equal to the multiplication of the u vector transposed times the v vector, which is also, we can write it in this form as well. It's just component by component multiplication all summed up. Once we define the inner product, we could define the length of a vector, and that's the non-negative scalar denoted with these absolute value signs of the square root of v dot v. We said that a vector whose length is 1 is called a unit vector, and if we divide a non-zero vector v by its length, then we obtain a unit vector, and this process is called normalizing or normalization. We also define the distance, so the distance between u and v, written dist uv, is the length of the vector u minus v. And then on a kind of different topic, but also about inner products, we talked about orthogonal vectors. So orthogonality of vectors is how we generalize the concept of perpendicular lines in ordinary Euclidean geometry. So we say that two vectors, u and v and Rn, are orthogonal to each other if u dot v equals 0. And we noted the 0 vector is orthogonal to every vector in Rn, and also we had this Pythagorean theorem, two vectors u and v are orthogonal if and only if the length of u plus v squared is equal to length of u squared plus length of v squared. Our last topic was about orthogonal complements, which we introduced in this chapter, but we'll use it later in a chapter when we discuss singular value decomposition. So the idea is if a vector z is orthogonal to every vector in a subspace W of Rn, then Z is said to be orthogonal to that subspace W. And the set of all vectors Z that are orthogonal to W is called the orthogonal complement of W, and we denote that as W with this little perpendicular sign as a superscript. And we read that as W perpendicular because this is the perpendicular symbol, or W perp. And then we have the following facts. A vector X is in W perp if and only if X is orthogonal to every vector in a set that spans W. And W perp is a subspace of Rn. And last, we have this theorem, which I have written in this form here. It's easier to read. If A is an m by n matrix, then the row space of A perp is equal to null of A, and the column space of A perp is equal to the null of A transpose. So that's it for this video. Thank you for watching.